Hey, good morning, everybody. So this is actually my new favorite image of DigitalGlobe. It's from Worldview 3. Some of you maybe saw it yesterday at SAT Summit. It's really cool. This is an image taken while the satellite was over, I think, the west coast of California, or just over the Pacific, looking at Colorado. So this is kind of like a third of the landmass of Colorado in one shot, looking incredibly high off nadir. You can see I think you could see Denver, you could see Crested Butte, you could see a ton of Colorado. It's super cool. But I'm not here to talk about this one image. So every day, we collect about 3.5 million square kilometers every single day. That's a ton of pixels. We have a bunch of satellites orbiting around the globe. A lot of people, yes? Can you not hear me? I'm going to do this. I'm going to do this like a rapper. So every day, I think with the elbow up, this is how I roll. So every day we collect about 3.5 million square kilometers. So a ton of pixels, a ton of data being downlinked from space. I'd like to talk to you a little bit about what that looks like from a data volume perspective, but also from a coverage perspective. So these are our collections over the last 3 days. Each one of these little orange strips is a collection captured during the last 3 days. Pretty cool. Over the last 2 weeks, over the last 3 months, right? As you can see, this coverage is global, it's persistent, and it's constantly running, 24/7, orbiting the globe. Now, a lot of people have talked about big data, right? My title says something about geospatial big data. Let's talk about that a little bit. So big data is a ton of transactions, a ton of bits of information. N gets large, we can process it, we can build models, we have Hadoop clusters that make sense of it all, we have elastic MapReduce, we have all sorts of this crazy functionality to make sense of all this data. I'd like to talk to you about a new concept. I call it heavy data. And that's a lot of what we're dealing with. Let's dig into that a little bit. So Landsat 8 is about 15 meters ground spatial density. The average scene size, 180 by 185 kilometer, whatever, is about half a gigabyte for the visual bands. Planet Labs doves between 3 and 5 meters. It's about 16, 15 gigabytes. Somebody can raise their hand and correct me, but I think I'm within the order of magnitude. A Worldview 3 shot is about a terabyte. And I actually included in here, here's an example of what it looks like. So this is a Landsat Pixel. This is a this is a Landsat Pixel of a certain object. This is actually off of near Niagara Falls, just a random spot that I had imagery from the gallery here. This is a Planet Labs image of that same object. And this is a Worldview image from DigitalGlobe satellite. It's about 60 times larger than Planet Labs and about 1,900 times the size of Landsat 8. Now, this creates unique challenges. Downloading an image strip is incredibly painful. I die a little bit inside when somebody FTPs a file. Just a little bit of me dies inside. We must stop it. We must get the data out of jail. So this is where we are. This is Washington, D.C. Hold on, there's the mall. I think we're like here somewhere, right? Somewhere in the middle of the image. This from a Worldview image. This from a Worldview satellite. So if you actually look at it, and this is actually this is an unrefined, our Photoshop people haven't touched it. This is straight off the satellite. This is kind of what it looks like. You can see a little bit of, those are shapes. Those are probably the shadows of people. You can see the cars. You can see the sunroofs. And we're actually in this building right here. It looks much better on my screen. That screen might be better. Now, it's not just one shot. So leveraging our Geospatial Big Data platform, we're trying to give access to all the data, to make it accessible. If people can't get access to it, it's dead to me. That's what we've discovered, that if you can't get it, it's dead to you. If you can't get a login, it's dead to you. If you have to spend 16 years waiting for it to download,
dead to you.
Dead to you, exactly, right? So this is through our platform. I just did a search around DuPont, right? Just a small little area. We have close to 500 different materials, 500 different collections over this exact same region. And most of them are actually over the last few months, over the last year, et cetera. And actually, you could do a search across filters, right? I want this off-nadir angle, this nerdness, sun angles, and all sorts of cloud coverages, and all sorts of nerdy different filters that you'd want to do. But the idea is to make it rapidly accessible. And you notice here there's a little Landsat switch. That's courtesy of Amazon Web Services hosting the Landsat 8 archive, where now we actually, through the same catalog, we can provide visibility, access, and processing of the of the Landsat catalog as well as the DigitalGlobe catalog. But it's not just about data. It's about extracting information from imagery at scale. So I'm gonna say a sentence kind of really carefully here. So we could always see anywhere on the globe. We could zoom into an intersection in Baghdad, or zoom into an intersection in Southern California, or look at a crop field in Iowa. We've always been able to do that. Cool, we could always see anywhere. The opportunity is to see everywhere. I want to be able to know what's going on inside each one of these pixels, and I'm pissed off that it's so hard to do it. There's so much value locked inside those pixels. Let's talk a little bit about that. Traditionally, we've done show me their applications. Show me that one intersection. Show me that one border crossing. Show me that one city square. The opportunity now is show me where. Show me where things are changing. Show me where the remote dwellings are located. It is a crime that in 2015, we still don't know where most of the world's population lives. Show me where all the vehicles are. This is actually a real use case where we've had customers automatically pick out cars from these data sets to detect traffic patterns. So the same thing that keeps you stuck in traffic in the morning is a gold mine for billboard advertisers if you're trying to quantify the value of billboards. Show me where all the new construction is. Now, there's some remote sensing nerds in the audience, maybe myself included, but a lot of people might say, it's like, Shay, actually, that's an impervious surface mask. We actually know how to do that. And that's exactly right. The algorithms are not the hard part. It's applying them at scale and being okay with imperfection, because you can't look at any pixel anymore. Show me where there's change. This is actually a real example around where a pipeline was an oil transportation pipeline, where they're trying to identify what the pressures need to be based on the risk to the surrounding population. And so they want to identify growth around the pipeline. And also and what that changes. So it's actually really important. And as we talk about different resolutions and different temporal resolutions, spectral resolutions, spatial resolutions, the key thing is to use the best tool for the job. So if you're just looking for growth of cities, you can use a lower resolution sensor to guide the higher resolution acquisition. So I'm going to channel a little bit of IBM here. So every day we create 2.5 quintillion bytes of data. And I have to confess, for somebody with data in their title, I should probably know how many zeros that means. But the key point here is that 90% of the data in the world has been created in the last 2 years alone. And we're not just talking about DigitalGlobe data. There's data from the sensors in your pockets. There's data from drones, from aerial mapping people, from Foursquare, from Planet Labs, from skyboxes, from USGS. This is only going and accelerating. There's a huge opportunity to not just understand one data set, but to bring them together. So I'm going to show you an example. This is kind of a federal, kind of a security application, because we're in Washington, D.C. I figured it would be topical. But if you remember from Crimea last year, about 18 months ago, there was a lot of violence, a lot of protests, and a lot of action happening in that region. And so what we did was we actually took Twitter data, and in an effort to zoom in from our satellites on the most relevant parts of the world and the most relevant parts of the region, we used the Twitter data in order to drive our collections. So these are our overlaid collections. Now, once you have the data, now it's all about processing. And so we ran the images that are collected through our Geospatial Big Data process, and we were able to identify roadblocks, military vehicles, and mind you, nothing, and I repeat, nothing replaces an expert analyst, but we're not trying to, because an expert analyst is not going pixel by pixel to try to understand it. There's just simply not enough capacity. So we're trying to identify regions of interest that we can then follow up on. And I really want to show you this next example. This is actually one of the hits that we had where we identified from space this roadblock and this tweet at about the same time. And now, pardon my Russian, Я не говорю по-русски. It says blog post, which I think is a block post. Anybody speaks Russian can read the rest of it, but that's all I have. So it kind of aligns. But notice kind of the tweets driving the collections and GBD interpreting the collections to identify regions of interest. Super cool. Now, this isn't just happening once. This is happening around the world. This is the opportunity. We need a little bit of help. We need help with this because it's not a trivial task. So, number one, nobody wants to download terabytes of data of high-resolution imagery. Okay? So we have a solution to this. And that solution is putting it in the cloud to make it accessible. Because if you can't access it, it's dead to you. Number two, nobody can afford it. If you want to do an analysis over all of California, get out your checkbook. But you don't actually want to own the imagery. You just kind of want to torture it for a little bit. You just kind of want to squeeze a little bit of value for your purpose. And understanding these two, we kind of have a new model going forward. So this is what we call our Geospatial Big Data platform, which is super simple, super simple. The idea is we have a factory, and we have about 16 different ground stations around the world. And we have our own data center that's chunking out imagery, converting it into 1Bs. We built a giant UDP accelerated pipe into the Amazon cloud. And now, as Jed so eloquently provided, we can bring the compute to the data rather than the data to the compute. Right? So instead of download, remember I told you I die a little bit inside whenever somebody logs in via SFTP. Makes me a little bit sick. Now we no longer have to do that. Now they can process the data where it's living, where it's at rest. And this is not a trivial process. And so what we've done is we've taken some of our own DigitalGlobe tools, like if you want to detect cars, or if you want to do land classification or vegetation detection, or some very basic feature detection tools. You're welcome to use the APIs to do that. We've teamed up with our friends at Envy at Harris to bring another 200 or so Envy Services Engine routines that now reside next to the data. Super cool. But if you don't like any of those because maybe they suck or you like to tweak it a little bit differently, you're welcome to bring your own. It's actually kind of cool. You can bring arbitrary algorithms and run them next to the data. Not trivial. This is what we're working towards. And this is all running in the cloud. It's a huge opportunity. Let's actually dig into a little bit of the system architecture of what we're talking about here. Let's geek out just a little bit. So, yeah, please. So basically now you have a view API. You can view an image, totally. You can now search the archive via an API. You can get access to the imagery via the API. That's the catalog API. Now you don't want to just look at an image, you might want to process it. You might want to process it. So use the workflow API. And what we've done here is we've tried to, you said the undifferentiated heavy lifting. We've tried to take care of that. So instead of you figuring out, oh, how many nodes do I spin up? Or how do I manage the data? What if one times out? How do I recover that, et cetera? We've kind of taken care of that and just kind of encapsulated some basic Amazon Web Services functionality into the entire workflow stream. And we're leveraging Docker Hub in order to allow you to submit your own algorithms to it. It's actually really simple, but incredibly powerful, the flexibility available to it. It's actually pretty sweet. And just double-clicking a little bit on the workflow API, I think one of the key opportunities here is that you don't have to be an expert in remote sensing and algorithm development and computer vision and DigitalGlobe specific satellite sensors and AWS compute infrastructure and big data, which is traditionally what we had to do. We tried to lower the barrier so that you don't have to be an expert in AWS. You don't have to be an expert in the big data stack. You don't have to be an expert in the remote sensing toolboxes. But rather, we're trying to make it much more accessible. We're at the infancy, but it's actually really, really promising. And so you notice here I have Landsat 8 and S3. A lot of everybody using this platform, we're in closed beta right now. We have some really, really interesting use cases, interesting customers. Take a look at our press release or our blog. We talk about some of these individual use cases. But what's really, really interesting is that they're all bringing their own data sets. They're all either bringing their own data sets or combining multiple data sets. And so it might be low resolution imagery. It might be social media data. It might be surveys of people on the ground walking around with clipboards and asking questions. But the key opportunity here is to make sense of all this data and putting it together. So I want to actually show one example. This is really cool because our intern did this over the summer. We kind of encouraged our interns to have their own projects just for fun. And so she kind of came up with, hey, I want to see what the effects are of the drought in California and the water restrictions. And are people actually abiding by it? And so I'm not going to go into kind of the results of the analysis or the details, but she did this in like 2 weeks, over 4,300 high-resolution image strips, 30 terabytes of data, all sucked into the system through the APIs, running the workflow APIs, running this with the NV toolbox to identify and quantify the rate of water usage. And so what she was able to do was take both kind of standard multispectral processing, NDVI with some clever thresholding, build a model, take additional county records, water company estimates, put it all together in order to create this chart. Now, this is where I might need your help a little bit. So one of the things we're struggling with is on the show me where applications, you need to be okay with messy data. You need to be okay with imperfect observations. N is big, but N is not sampled every 3 hours. And so how do you interpolate between that? You can't see everywhere at once. So you can leverage some lower resolution sensors, absolutely, to fill in the gaps, but you still need to build a model that takes in high resolution observations, low resolution observations, on the ground data sets in order to make sense of it. It's actually a huge opportunity, but it takes another layer of thinking. When you subsample, the observations, when you have imperfect machine learning, you still can make sense of it better than ever before. But it's not the same thought process, it's a little bit different. So for example, if somebody says, hey, Shay, I want to see this one port every day this week, honestly, we struggle with that because security applications are going to trump you. It's going to be too expensive for you to get access to that. But 16,000 ports around the world, I probably see 40% of them every week, 60% of them every week. Can we build a model to estimate global imports and exports based on these imperfect observations? Actually, yeah, we probably can. So anyway, so this is kind of the challenge to the room. These are, you guys, I see you as kind of the most interesting folks in terms of the applications, in terms of technologies. If all we do is steal market share from each other and like the different SAT players and data providers, like whatever, this industry is dumb anyway, right? The opportunity here is in blowing it up, is in making these use cases applicable beyond the remote sensing and niches that existed in the past, but rather answering true business questions. So this is a good time for me to get into questions, and for you, feel free to also tweet at me if you don't want to speak publicly, and I'll answer your questions when I sit down. I heart crowds. I do like them. So I'm going to pause right there for questions.
How do you get the private developer data access right now?
You're welcome to email Big Data. We're collecting emails and we're inviting folks. We're working with some of our best partners and customers right now and onboarding them and having them tell us where we're dumb, where we're smart, what they want to see in it. It's actually pretty sweet. Yeah. So GeoBigData at DigitalGlobe.com or tweet at me.
You mentioned some of those tools to simplify accessing the data. To what extent are those generic and could be applied to other large data sets that happen to be residing on Amazon, for example?
A lot, yes, absolutely. So a lot of the tools that have been created, like for example, the NV toolbox is not particular to DigitalGlobe's imagery. A lot of the pre-processing routines is not specific to DigitalGlobe imagery, or not imagery in general, period. And so there's a lot of opportunity to apply it. Not everything is push button applied to any data set that you want, right? Like the Nextrad weather data. If you try to do land classification based off that, it'll blow up, right? Obviously. But yeah, we are trying to put it under one roof to make it much more accessible for that. Also, some of our key learnings, I'm not really able to announce it, but stay tuned. Some of our key learnings as far as how to move around these giant data sets, how to process them, how to provide pseudo-random access. We're going to be open sourcing a toolbox to try to hopefully encourage others to use because we really want to, honestly, this is about pushing the industry forward. It's not about us versus them. It's about kind of all of us actually making a dent in kind of the commercial, government, federal applications.
Will you be able to get some of the results of these processes off of the cloud? For instance, if I have a sensitive data set that I don't want to put up there, but I have some output from the imagery that I want to compare it to?
Yeah, so that's kind of the realization that we had. That's actually a really good question. The question was around, can you get the products out of the system? And that's exactly kind of the realization that we had, is that people are downloading the data, torturing it, and making it into a spreadsheet, or making it into something much lighter than it was what went in. That was kind of the realization. We want you to be able to, download via HTTP a simple product derived from the imagery. So absolutely. However, what we are seeing is a lot of people are kind of building their algorithms and then just kind of plugging them into the pipe and using it as the data is downlinked, and they're just leaving all their processing in AWS. So they might move it to their S3 bucket where they ingest it into their own data store, their own database in order to make sense of it and combine it with other data sets. So yes, and also, you kind of brought up an issue of security. Absolutely, the algorithm is yours, it's yours, it's yours. Many cases, we don't even get access to look at it. We just know how to run it. We kind of have the protocol for mapping inputs to outputs, and you can submit it via a Docker container, and we just know how to turn on the juice. I love the question. So on the California example, it's like, hey, Shay, how long does it take to do atmospheric compensation and NDVI with thresholding? I don't know, about 14 minutes. What if I have 4,700 strips? How long will that take? I don't know, about 14 minutes. And that's kind of the beauty of it, right? Is being able to run this at scale where it's not just show me there, it's show me where.
What kind of capabilities you have for auditing or provenance tracking as you go through the process, right? So you do a process. How do you make sure that that's a repeatable process?
Repeatable in the sense of the algorithm giving you the results you expect?
That you know which data and which algorithm
Sure.
apply to that.
I think that's a good question, and that's actually a little bit of a complicated one. And let me actually double click on that a little bit. Kind of a lot of the value that we're seeing is not just one algorithm applied, but a collection of them. Like we had, I'm going to kind of be transparent here, we had an issue with car detection over this one road in an Asian country. Why? Because bushes were being confused as cars, because they all kind of looked the same. And there are regular intervals. Okay, so one way to deal with that is by being really, really annoyed about the lack of, about the accuracy of said algorithm. Or another way is to combine it with the vegetation analysis algorithm. Don't look for cars on top of trees, right? And so in that sense, you can put probe points in the middle to kind of see intermediate outputs. So we're trying to provide visibility into where stuff has failed and intermediary outpoints throughout the chain. But this is something we're going to keep iterating on. And it's not just how to do it, it's how to make it simple and intuitive. It's not trivial. Yeah. Oh.
Have you figured out a good way to handle version control for algorithm development and like training data sets and output data sets and just sort of like the whole workflow for that mess of data and code?
So on algorithms, yes. On data, no. I'm open to ideas. No, we have some teams working on it. But on the algorithm development, yes, and kind of version control within Docker Hub and knowing which version was submitted when by which user, et cetera. If you've ever built kind of your own experiment or algorithm, you end up tweaking, right? Different parameters, different default parameters. It's not a very healthy process. But keeping track of these tweaks and what the results are is something that we're going to need to work on. But so it's kind of up to the user, right? It's an API that they need to keep track of. On the algorithm actual submission, it is being tracked. Also, I would say, one of the functionalities that we've created is actually graph database structure, and so digging in a little bit under the hood, because we want to be able to track that these car detections, vehicle detections, or vegetation analyses were derived from this collection of images that were derived from this sensor combined with this other sensor that was histogram adjusted based on the output of Landsat, that was derived from, right? You want to be able to track kind of the lineage of the outputs. And so that's actually built into the core of the system. You asked specifically about the version control, and my architect would have a better answer about the tracking the outputs. The outputs are all tracked, but those specific versions from that specific run, we could talk about. Cool. Well, thanks for having me. Feel free to chat. I'm here all day.